Hi all, welcome. So thank you for joining our live stream and thank you for trying this out. I'm really excited to be doing this. So I'm going to cut over to the Jupyter Notebook. Okay, so here we are. So hopefully everybody's set up and has the notebook in front of them, either in their own environment or through Google Colab. Google Colab is actually, it's pretty simple to use if you find that easier to work with. So this is a workshop, brief workshop on StructureBoost, the introduction of StructureBoost. StructureBoost is a gradient boosting package that can exploit the structure of categorical variables. Hopefully most of you have had a chance to watch the 15-minute video that I sent out previously. If not, here's the link. Don't watch it now, but you can maybe watch it after we're done here. It gives a good background of what we mean by categorical structure. And so by the end of this notebook, you should, again, have reinforced this notion of what a structured categorical variable is. And you should know some basics on how to configure StructureBoost and use it. We're assuming that this lecture is really aimed more towards people who have been using Python and have been sort of modeling and working with that environment for a bit. So hopefully you've had some familiarity with boosting, you fit a gradient boosting model before, and so forth. If you haven't, it's probably fine too. You can go through the notebook, you can understand what's going on. It's all pre-filled out. So you really just have to shift enter through the cells of the notebook and you can still get a lot out of it. Here's going to be the link to the stream and the link to the channel. If you really want to get into details, here are the couple of the more academic papers that are behind this. The first of which is in the AI Stats Conference, which is being held online in just a couple of weeks. And the second is on arXiv. And there's also documentation for the code. So again, to get started, a couple ways to do it. You could clone the repo. Here's the address, github.com numerical resources, and use your own environment. Make sure you install StructureBoost, which should be very straightforward using pip. The other option is to use Google Colab. You could just click this link if you have a Google account. It's totally free and easy to use. And you can get the notebook and the data from GitHub. So there'll actually be a cell which loads the data directly from a URL, and you can get the notebook. Google Colab has a way to basically open something in GitHub. So if you just I think you search for numeristical, it'll find the GitHub account. You should be able to find this notebook with this title and open that up in Google Colab. Okay. So this notebook is going to be centered around this one motivating problem, which is predicting rainfall in California counties by month. So it's a simple problem where you've got two categorical predictors. You have what month it is and what county you're in. And the goal is to predict what's the probability of rainfall on an arbitrary day in that month in that county. And this is a really good test example for StructureBoost and highlights the power of it because both county and month are categorical variables, which, as I'm sure you know, if you've worked with these things, categorical variables are always kind of difficult to work with. We have these nice techniques for numerical variables, and then we try to sort of shoehorn categorical variables into the same structure, and that's part of the reason we don't do so well in using that information. Another nice thing about this problem is that this is actual weather data from NOAA, which is like the weather service essentially for the US government. And we have enough data because we historically have data. I only got data back to 2000, but you could go back very far if you wanted to. You kind of know what the probability of rain in April in Riverside County is because we have enough observations in the past to say, of the 1,000 days that we've been keeping record, how many of them actually had rain. But then the challenge here, and where this highlights the power of the method, is that how could we perform if we only had a little bit of data? How well could we predict what the true right answer is? So this is the problem we're going to concern ourselves with. So there's 58 counties in California. I included a rather large map showing all the counties. But the key is that California has a lot of geographical variety. There's coastal climates, there's mountain climates, there's desert climates. And so different counties are going to have very different rainfall patterns over the course of the year. And again, our goal is we want to predict probability of rainfall given just the county and the month. So for example, what's the probability of rain in April in Riverside County? Now, one thing about this is that there's 58 counties, there's 12 months. So take 12 times 58, that gives you 696. So there's 696 month county combinations. So when we think about what's our model that we're going to end up with here, we're going to end up with 696 different probabilities. And that's what our model is going to represent. So anybody could kind of come along and assign 696 numbers to all these situations, and that would be a model. And we're going to judge the quality of our model by calculating the log loss on an independent test set. So log loss is also known as cross entropy. It's also equivalent to maximum likelihood if you're used to coming at it from a more statistical background. So this is a very common way to evaluate the quality of probabilities. So let's get started. So if you don't already have StructureBoost installed, you could uncomment this line and install it, or if you're on Google Colab, that'll also work to install it. It might take a minute or so to install. Here are a bunch of the packages and preliminaries that we'll be using. And then if you clone the repo, you should be able to read the data with this line. If you're on Google Colab, you should be able to uncomment this line instead. Don't use that line, use the commented line, and that should also work. And if you did it right, you'll get a sample of 5 data points. And if we look briefly at the data set, you'll see we have the county, the month, we have the actual date that we're not going to use the full date, the particular weather station where the recording was, the amount of precipitation, and then a 1-0 variable rained, and then just another key. So we're going to really work with county, month, and range. County and month are going to be our predictors, and range is going to be our target. And if we look at the shape, we have 415,000 total data points to play with. So the first thing to know is that this is actually a lot of data. We're estimating 696 binomial probabilities, and we've got about 600 data points for each. And since these events are not that rare, rain is not that rare. It's sometimes as low as a few percent in some cases, but for most months, 10 to 20%, something like that. So we kind of know what the answer is. This is just getting at what I was describing before, that we, using all the data, we can know what the answer is, but we're going to pretend we don't have all this data and that we only got a small sample of data and see how well we could estimate it and then compare it to the right answer. So what we're going to use as the right answer is just looking at the empirical estimate. So for each of those 696 month county combinations, we're going to get the count of how many days there are total and how many days there were of rain and make a little data frame out of that. So you see if we do that, and again, I take a sample, you see we have a month and a county, we have the empirical probability of rain, and we have the number of observations that was based on. So we're going to use that as that's the right answer, so to speak. And before we get into modeling, we're going to explore this data set a little bit to understand it. So I'm going to write a simple function that helps us plot and look at it. And here I'm taking 5 counties and I'm plotting their seasonal rainfall pattern. So 1 represents January, 12 represents December. And you see there's a lot of variety, right? So this topmost curve is Del Norte County. That's in the northwest corner of the state. It's the rainiest county. So you see it's over 50% in the winter and then drops down to about a little over 10% in the summer. By contrast, Inyo County is a desert county. That's actually where Death Valley National Park is, which is like the driest place in the country or the world, something like that. And you'll see there the rainfall is very low. But the other thing to notice about this data is if you pick counties nearby each other, they tend to have similar patterns. So here's 4 counties in the Northwest. And you see there's some range, but they're basically all in the same neighborhood of behavior. In the Southeast, these are the more desert style counties. So you see they have much lower rainfall and a very different pattern. In the mountains near the Nevada border, so here's 6 different counties that all have, quite similar behavior. Around the LA area, it's kind of similar to the desert, a little bit rainier. And in the Northeast, it's kind of like the Northwest, a little bit less rainy, but also similar behaviors. However, it is also possible to have counties which are next to each other and behave quite different. So if you look at Fresno County and Inyo County, you see Fresno is actually quite a bit rainier in the winter, but is actually then considerably drier in the summer. So these 2 counties border each other, but they have pretty different patterns. So what's our challenge? Well, the key observation I want to make is if you had enough data, you wouldn't really need a model. You could just say, I've got so much data on April in Riverside County. I'm just going to average those numbers, and I'll get a pretty accurate estimate of the probability of rain in Riverside County. So if we had our whole data set, we wouldn't need a model. We would just compute the average of each different possibility. But what if you only have 1,000 training points in total? So there's 696 month county combinations, and we've only got 1,000 data points. That means on average, you have 1 or 2 data points per month county combination. So then if you try to just use the empirical approach, you'd be in trouble because you only got 1 or 2 data points, and it either rains or it doesn't. So most of your estimates, if you have 2 data points, your only possible estimates are 0, 50%, or 100%. So that approach is not going to work if you've got sparse data. So more specifically, if I had 500 observations from Riverside County in April, I could just get a good estimate without knowing what other counties are near Riverside or what other months are similar to April. But when we have sparse data, you need to somehow average across these similar situations. You have to say, hey, I don't have that much data on Riverside in April, but if I look at Riverside and all the neighboring counties and I average together March, April, and May, well, that'll give me a little more data to work with. So what are the sort of standard approaches to this problem? Well, the standard approaches are usually things like using one hot encoding to represent the county. Or perhaps numerical encoding, you would just rank the counties from the rainiest to the least rainy and treat that then as kind of a numerical variable. And this is what things like CatBoost and LightGBM do. So CatBoost and LightGBM are kind of the latest entrants on the boosting scene. And they natively handle categorical variables. That's what sets them apart from, say, XGBoost, which was previously the most used, I would say, boosting package, and probably still is. But CatBoost and LightGBM, what they are doing is they're still taking that categorical variable and pushing it into a linear structure. They're doing some clever things to find a good linear structure and to not overfit too much. But at the end of the day, they're still treating it as a linear structure. And as we see, the 58 counties and the 12 months, neither of those things have a linear structure. So we're going to suggest here a new approach, which is to really define the structure of your variables and use StructureBoost to perform boosting on it. So we're going to set up our training, validation, and test sets. So we're going to use train test splits. And all I'm doing is I'm making a training set of 1,000 points, a validation set of 10,000 points, and a test set of 100,000 points. And to explain how I'll be using these, so the 1,000 points is what we're really going to learn from. The 10,000 point validation set is just to let us know when to stop our boosting so that we can use early stopping. And this just helps us avoid, when we're comparing models, helps us avoid any criticism around, oh, you found good parameters for this model. How do you know the same parameters are the right ones for this other model? Helps reduce some of that uncertainty. Okay. So one thing about StructureBoost is that it has a much more complicated configuration than most other boosting packages. And we're not going to go through all the details now, but some of the most important aspects are that first you have this feature configs dictionary. And this is just a simple Python dictionary. And the way it's structured is the keys of the dictionary will be your feature names. And so when you call fit, it's going to look for every key in your feature configs dictionary. It's going to assume that's a feature and look for that column name in your xtrain data frame. So StructureBoost, it doesn't, unlike other packages you might be familiar with, usually you call fit on X and Y, and it just assumes that every column in X is a predictor to be used. StructureBoost doesn't work that way. StructureBoost looks at the feature configs and just pulls out the column names that you specified and only uses those columns. So that's how it defines it. It doesn't use the order of the columns. It relies on the names, and it relies on the names as defined by the feature configs. So this is a little bit more work, but it allows us to have much more flexibility and put in these feature-specific configurations, which is often not possible to do in some of these other packages. Okay, so to get started, there's something called the default config dict. This is just a dictionary that specifies some default values that we're going to use that we can then override later as we build this configuration. So this is the main first line I want to bring your attention to. And the idea is you want to build this configuration file. You don't want to type out this dictionary from scratch. The easy way to get started is you just call this function get basic config, and you give it your train set, and you give it this default dictionary. And it'll give you a first pass at trying to define a dictionary. So you see when I call this basic config function, the dictionary I get out has two keys, county and month. And note that the values for corresponding to those two keys are each themselves dictionaries. And so for county, we're saying that the feature type is categorical string. That means we want this to be a categorical variable, and it's going to be, the values will be strings as opposed to integers or floats. And there's a graph, we can't really see what it is, but there's a graph object now associated with that. And by default, what this basic config function is going to do is going to say, as my default graph, since I don't know what the structure is until you tell me, I'm going to just assume everything's connected to everything else. So really kind of assume no structure to start with. And then we'll be able to substitute in the graph that we want to over here. And then we also have specified the split method and the number of spanning trees, which is a parameter that this split method requires. And I don't want to spend too much time about this. If you saw the video I referenced at the end, there's kind of two ways that StructureBoost handles these structured categorical variables. One is by spanning trees, the other is by edge contraction. So the default method is going to be to use a spanning tree and to just use one. And you can override these all later if you want to. For month, it said, hey, I looked at month and it seems to be a number. So I'm just going to treat it as a number. And I'm going to specify that the max splits to search is going to be 25. So this is just a starting point, and then you can override these with whatever you want. But it saves you the trouble of having to kind of type out this initial dictionary. Okay. So let's look at what this graph object is. So we've got this graph object over here. And if you want to see what it is, you can just assign it to a variable and then look at it. And so StructureBoost has its own graph library underneath it. And again, here by a graph, what we mean is vertices, which are just dots, and edges, lines connecting the pairs of dots. So for example, for the 58 counties of California, we're going to have one dot. We're going to represent this by a graph where there's one dot per county, and there's a line between two counties if they border one another. And if you see what this line is supposed to show you is that the graph that we're starting out with has 58 vertices, has 1,653 edges, and 1,653 is exactly 58 times 57 divided by 2, which if you remember your combinatorics, that's how many pairs you would have if everything was connected to everything else. That's how many distinct pairs, unordered pairs there are of objects. So this is our default configuration because this is what we assigned, not knowing anything about what those words mean. It just saw a bunch of words, bunch of strings that said, hey, I found 58 different strings. I'm going to create a graph where those are the vertices and everybody's connected to everybody else. But we can use this as a starting point. We can run StructureBoost using this. And so that's what we're going to do here. So StructureBoost, for the most part, uses the same paradigm you're familiar with from scikit-learn and things like that. You define an object with a bunch of parameters, and then you call the fit method on that object using a x and a y, and perhaps some other parameters, and then you call predict. So first we're going to define it. We're going to say, put 2,000 trees and a learning rate of 0.02. And I do this on purpose because I don't really think we're going to use 2,000 trees, but we're going to rely on early stopping to choose the right number of trees. So I can just put a big number and a relatively low learning rate, and it'll stop at the right point based on the validation set. And then I pass this feature configs, which is the dictionary that we need, that we just defined up here. And that tells us what our variables are and what kinds of variables they are and how it should treat them. And I'm going to put a max depth of 2 and tell it explicitly that this is a classification problem. If you do a shift tab, you can see there's lots of parameters. I'm not going to go through them all, but it is pretty well documented if you want to understand what are the other options you have. So I'm going to call this, and now I'm going to call fit. And I'm going to specify an eval set. I'm going to say look at x valid and y valid to decide when to stop. And I'm going to put an evaluation frequency of 20, which means check every 20 trees, check your value, which it's going to check the log loss of this validation set. And then early stop past steps means 1 says, if you're worse than you were 1 step ago, then stop. So this is a very quick, kind of a quick trigger to stop, where it's saying, hey, as soon as I'm worse than I was before, I want you to stop. And again, the number of steps refers to the evaluation frequency. So here, a step is 20 trees. So it's going to check at 120. If 120 is worse than it was at 100, it's going to stop. Otherwise, it's going to keep going. At 140, it'll check again. If 140 is worse than 120, then it'll stop, and so forth. So let's run this. And you see it stopped at 200 because the number at 200 was higher than the number at 180. So that's why it stopped there. And now we can get the predicted probabilities. Predict is a little bit slower in StructureBoost than in other packages. It has not yet really been optimized, so that's part of the reason. One other thing to point out is that predict in StructureBoost gives probabilities. It does not give hard 1-0 values. So if you want hard 1-0 values, you can always threshold them after the fact. But I really want to enforce the mindset that your primary prediction should be to get the probabilities. And now let's look at our log loss. So we get this number, 0.4222. So that's good. And that's what StructureBoost gets without using any really structural information. We haven't told the model yet anything about which counties border which other counties. So that's what we're going to do next. So next, so I'm going to call this is going to give a very big cell, right? So if we look at these edges, this is just to show each of these rows represents an edge, and you see every county borders every other county, no matter whether they actually border each other or not. And to give a little insight, just a little practice in how this graph object works. The way this graph object works is pretty simple. You could give it a list of vertices, and then a list of pairs of vertices. And then you can make a graph by calling this stb.graphs.graphUndirected with the edges and the vertices. And you'll see we make a new graph that has vertices A, B, C, D, and these edges. So if you had some categorical variable that you wanted to work with and you wanted to build the graph from scratch, you would do it by, you'd list all the values of your categorical variables here, and you'd list the pairs of which ones are bordering here, and you'd use that graph in your feature configurations. So California graph has 58 vertices and 133 edges. Rather than going through all the trouble to type all that out, it's actually, I included it in the StructureBoost package. There's a few graphs. There's like the US graph is in there. A couple other things are in there by default. And what you'll see is, so we have stored essentially this graph. And if we look at it, you'll see now we've only got 158 vertices and 133 edges. And if you look at these pairs, all of these counties actually border one another in real life. And now what I'm going to do is I'm going to take our old feature configs, the one we just used, this feature configs default. I'm going to make a deep copy of it. And then I'm going to replace the graph used under county with the graph up here that I just made. And now if I compare the two feature configs, you'll see they look identical, but the only difference is the address of the graph. So they're using different graphs. And the graph that feature configs 1 is using reflects the actual geography of the California counties, whereas the one that the default configs is using represents a world where every county bordered every other county. And again, just to compare, so feature configs 1, the county graph has 133 edges, whereas default had 1653. Okay, now let's do the same thing we did before, except we're just going to use this new feature configs object. I'm going to fit it, let it go, finished, predict our probabilities, and look at the loss. And you see we improved on the loss quite a bit. We went down from 0.4222 to 0.4167. Our first model used month as just a number from 1 to 12 and used county as a categorical thing, but didn't know anything about its structure. So it just said, this is just a big blob of categories where everything is connected to everything else, that there's really no structure there. Then we said, okay, let's take it county, let's actually give it the geographical structure. So we added in this county graph with the structure of the counties, and we got an improvement in our log loss. Now we're going to take month, and we're going to say, you know, one thing with the month of the year is that January and December are actually adjacent, the same way that July and August are adjacent. So while you can do okay by representing it as a number from 1 to 12, it's really more appropriate to have 12 also be connected to 1 and kind of have a ring-like structure. So let's do that here. So we're going to do that. And again, I made a little tool to make it simpler. So rather than having to sort of type in the graph with 1 through 12 and making these little sets to make sure that the neighboring integers border each other, you can just call this function cycle in graph. It'll make a cycle for you. So here now we have a cycle of numbers from 1 to 12. And so now when we create this new feature configuration, we're going to say actually month is a categorical integer, and I want the graph to be this month graph that I just defined here. And then I'm going to use this thing called apply defaults, where I say, you know, and again, this is a simple way to try to save you a little bit of trouble. If you don't really know what you want to do for those other more advanced parameters, you could just call this apply defaults, and it'll put in the default. So when I call this apply defaults, it now says, oh, you had a categorical integer, and you didn't tell me what split method to use. I'll fill in a split method and the appropriate parameters for that. But again, all of this is just tooling to define a Python dictionary that looks exactly like this. So you could just sit down and build up a dictionary from scratch. Start with a blank dictionary, add in this, make these smaller sub-dictionaries, and then build up the big dictionary. You can do that just, it's a little bit tedious, but if you have experience with Python dictionaries, it's not really that hard to do. So now we're going to run StructureBoost where the county knows the geographical structure. And for the month, it also knows that it should have a circular structure. And we're going to run the same thing. So again, you see it ran down until the log loss started going up. And you see we get another pretty substantial improvement in log loss. So our first one had 4222, this one 4167, this one 4108. And now I'm going to compare with CatBoost. So CatBoost, again, handles categorical variables natively. You can just tell it, treat this thing as a category, and it will essentially try to find the best linear encoding of it. So we can try CatBoost where we say, treat county as categorical, keep month as a number, and run it. And you see the results are not very good in this case. It's actually worse than our default. We're going to run this a few times later. We're going to run multiple trials and average it to make sure that it's not just the coincidence. I think this is kind of a bad result for CatBoost. I mean, most of the time it's going to be pretty close in performance to the unstructured StructureBoost. And we could also try, what if it used both county and month as categorical? And there you see, in this case, it does a little better. And so we see, here's the summary of the results. So you see that the CatBoost, and this is a little bit anomalous, we'll see when we run the full multiple trials. More typically, the two CatBoost variants are kind of close to what StructureBoost does with no structure. But then clearly adding in this structure, the county structure, and then the county and the month structure improves your performance considerably. And now, when you're looking at log loss numbers, it's not always easy to tell, like, is this significant? Would I notice this? And so forth. So let's actually start looking at what the model predictions are between different models. So I made a little helper function that you could give something a list of models and give it what county you want to look at and give it kind of the right answers. And it'll compare the two models. So here, model 0 is going to be the CatBoost, model 1 is going to be the StructureBoost. And we're going to look at Riverside County and compare. And so you see the actual is down here, right? Riverside is one of these desert areas where Palm Springs is. And so you see it's quite dry. And you see that, StructureBoost, does okay. It certainly notices that it's drier than average and kind of roughly gets the pattern. CatBoost does not really. It kind of gives a very average performance. And in fact, what we're going to see, I'm going to do these next two counties. So if you look closely, you see CatBoost is not varying its prediction very much for different counties. And so, for example, these first two counties are about as different as they come. Riverside is one of the driest counties in the south, and Del Norte is I believe, the wettest county, and it's in the north. And the predictions for CatBoost barely budge. I mean, they don't really move very much. You see, it's around 0.3 for January and February in both cases. It goes down to about 0.1 in the summer, and then goes back up. And you notice another thing, right? It kind of has a big gap between December and January. So that's another thing you might notice about it. Whereas if you look at StructureBoost, when it's at Riverside County, it's considerably drier than average and drier than CatBoost predictions. When it sees Del Norte County, it's considerably wetter. Again, it doesn't have enough data to really realize how extremely wet Del Norte County is. But it's able to learn from the neighboring counties that this area is wetter than average. And here you see Mendocino, and this is an interesting one because Mendocino is wetter in the winter, but pretty dry in the summer. And you see that StructureBoost kind of got that. It's pretty overall matches the curve pretty closely, including that it's wetter than average in these months and drier than average in these other months. And again, CatBoost doesn't really do it. And it's not, if you think about it, it's not surprising. CatBoost doesn't know the geography, and we have very, very little data. So we only have 1,000 points. So if you don't know anything about the geography of these states, we have just very few observations with which to use this information. You've got 58 counties and you don't know where they are, and you've got a handful of observations scattered amongst a bunch of months. It's going to be very hard in the absence of that geographical information to come up with good predictions. Okay, so I'm going to let this run. This is the same thing, just running 5 trials of all the different models and getting the answers. Okay, so this finished. So let me just put up these numbers quickly. I see some more questions coming in. Okay, so again, so for people who are wondering, is this improvement really significant or not? Is it important? So here I averaged 5 trials so that you could really see, get some of the noise out. And you see again, CatBoost, first of all, CatBoost does better treating month as a number than treating month categorically. But it still does about the same as StructureBoost with no structure. Does a touch better in this case. But you see that StructureBoost incorporating the county structure takes you down a significant amount, and then incorporating the month structure in addition takes you down even further. And if you look at the AUC, which people might have more of a sense of how much of a gain in AUC is good, here you see a pretty stark difference, right? So with the county and month structure, you get an AUC of 0.751. When you had no structure and StructureBoost, you had 0.734. CatBoost gave 0.728. So it said between 0.751 and 0.728, and that's averaged over 5 trials. That's a pretty significant difference. And I gave some cells here just where you could look trial by trial, what was the discrepancy. So is it, and what you see is that, it's consistently between 1.6 and 2.8 points better on AUC. So, it's not just, the variance has kind of settled down. It's consistently better trial by trial. Okay, well, again, thanks very much for joining me today. Some final requests: if you could like and subscribe the channel. Trying to get to 100, then I could have a name channel, so that'll be pretty exciting. If you use my GitHub repos, if you could give them a star, that would be appreciated. I'm going to put some new classes up, and I'll post out about them again. I'll probably send an email out to this list as well as on LinkedIn and the usual channels. And also, please tell other people who you think might be interested that they could, both about trying to come live to the classes or even just watching them offline. It would be great to just kind of build up more of a following and be able to find interesting subjects to talk about. Okay, thank you very much.